um, from Xan Danes, Endress Hauser, and Patrick Rounds with Miller Mechanical. Zane, you want to kick it off?
Yeah, if you're ready to get started, we can roll right into it. My name is Xan Danes. As Grant said, I work for Endress Hauser, and this is something that, frankly, I have a lot of passion about. It's something that seemingly every day, every week, we can learn more and more, especially as call them newer radar frequencies are being developed. I like these ISA type presentations because it really allows me to focus on the technology itself. So without even getting into anything manufacturer specific, just covering basic things like what's new with new radars? Why are there so many seemingly new radars? And then backing that up, not just with the fundamentals, but also examples of where these new radars come in handy, how they solve application challenges that may not have been possible even 5 or 10 years ago. With most new developments, there come particular examples of drawbacks or scenarios where maybe R&D or product development didn't think of where the devices may not be applicable. So I would like to share some of those as well. These call them absorption phenomena and what they mean with radar in particular. And then after that, I want to talk a little bit about what the future holds, what's coming in the next few years, what to expect, especially when it comes to non-contact radar developments, and then touch a little bit about how do you verify, calibrate, or proof test one of these devices. Before I continue, if there's specific questions, does your chapter typically ask them during the presentation, or should we hold Q&A until the end?
We usually keep it interactive.
Okay. I'll keep an eye on my other screen then. If anybody does have questions, either just blurt out or try to catch my attention somehow. Fair? Hard when I can't see everybody. My background, or where I'm coming to you from, I was a chemical engineer by education. My entire career has been as an instrument engineer, specifically focused around refineries and functional safety instrumented systems, some environmental projects as well. As of late, I've really been focused as a product technology manager for Endress Hauser. And what that means, or where the new developments tend to be, where I tend to focus, is on radiometric or nuclear applications and radar. So about 100% of my time is spent either working on ionizing or non-ionizing radiation. For today, all of this is non-ionizing radiation for radar. In order to explain some of these really fascinating coincidences, I kind of have to start from the ground up and just make sure that we all understand the basic variables at play with these measurements. So at its most basic, a radar measurement is based on reflection of microwaves based on a change of wave impedance. This change in impedance occurs at the interface between two different media. And all of my reflections, all of my change of that wave impedance is going to result in some type of reflection. We call it the reflection coefficient. What this is, it's really defining, if I shoot a microwave at something, how much of that microwave is going to get reflected back to me, is going to bounce back, versus how much of it's actually going to propagate through the material in question. The difference between the emitted, so the amount of microwave energy that propagates through a media, and the amount of microwave energy that reflects off is called transmission. And this is really dependent on the dielectric constant. So with radar measurement in particular, we're always going to be talking about this dielectric constant, which is a measure of the electrical permittivity relative to that of vacuum. Because we tend to focus, and rightfully so, the dielectric constant being so critical and the interface between two different dielectric constants, we tend to make some very critical assumptions that for the most part are valid. We assume that the propagation speed in all cases in any type of medium, it's going to be slower than it is in vacuum, but the speed itself really depends on the material properties. So we introduce this other constant. You see the dielectric constant of most gases, it's approximately 1. The other variable is the permeability. So how available that gas is to allow our microwave or our radar signal to propagate through it. And for most gases, for most vapor spaces, even in vacuum, it's approximately 1. So we say this is a safe assumption. We might even say for non-magnetic media, non-polar media, the influence of this permeability constant is negligible. So we operate under this assumption that the dielectric constant is the most important factor for any radar-based measurement. We essentially take that mu out of the equation.
Can I pause you for a minute?
Sure.
Can you briefly explain the difference between the epsilon and the mu, the permeability and the other coefficient? Is it like the epsilon is more to deal with the particles themselves and the mu is the spacing of them?
Not exactly.
Okay.
The dielectric constant or the permittivity is a measure of I call it the reflective properties to simplify it. And you'll see as I go through here, I do not mean to pass myself off as a physicist, because these values can get challenging to determine if someone else hasn't already determined them for you. So I think of the relative permittivity in terms of that reflective coefficient. I think of the permittivity as the likelihood of a material to reflect a microwave signal, whereas the permeability is the ability for it to transmit.
Okay.
In these cases, since we're dealing with all gases, so air, carbon dioxide, oxygen, nitrogen, SO2, for most of the things we would traditionally consider in the vapor space, our permeability and our permittivity are both going to be equal to 1. A few things physically that determines radar measurements, and in particular the viability or the installation of radar measurements in the real world. As we're looking at directing this microwave energy downward, we have to do so with an antenna. So we really have to design or look at the geometry of this antenna as a way to direct that energy downward, to take that wave impedance and get as much of that heading in a downward direction as possible. So what we typically assume, or in all cases is true, when I have a larger antenna, I'm able to get more of that physical radar signal into the vessel in question. So larger antennas allow a better adaptation of the wave impedance. But what we say more often than not is that when I have a larger antenna, I get a better directivity of that microwave energy. So when I have a larger antenna, I have less diffraction, I have a smaller beam angle, or you can say that the signal is more focused. There's another benefit, though, to having larger antennas, especially with non-contact radars. We don't just have to shoot this radar signal or shoot this microwave energy into a tank, we also have to catch it. So when I have a larger antenna, I not only have a more directed, more focused signal, but I also have a larger net. I have a larger aperture, a larger area to collect that signal, so more energy can be received. Traditionally, I was taught that for every nominal increase in antenna size, so going from 1.5 inches to a 2-inch or a 2 to a 3-inch antenna, every nominal increase, I effectively double the gain, the available gain of the measurement. So you'll see with larger antennas of a radar with a given frequency, larger antennas often result in narrower beam angles, but also larger measuring ranges. And in some cases, larger measuring ranges with fluids of lower dielectric constants, so less reflective media. It's pretty quick to observe the trends when it comes to non-contact radar measurement. Over time, not in a linear manner, but over time, you'll notice that the frequencies almost exclusively get higher. You might find some exceptions to the rule here, but if you look at the major manufacturers in this space, the first non-contact radars operated between 4 and 6 gigahertz, followed a decade and a half later with what was at that point considered higher frequency radars in the 24 to 26 gigahertz range. Now, when you hear the term high frequency radar, most people will jump to the 80 gigahertz frequency. But manufacturers, frankly, are in an arms race. So even this decade, we'll be looking at the next highest band, that D band or millimeter band, in the 110 to 300 gigahertz range. I'm going to spend a little bit of time explaining the why, and then we'll get into those few gotchas behind any new frequency and a big part of what I guess our job as stewards is today. The radars functionally or fundamentally, there's a couple things that don't necessarily change. If I look at the two commercially available level measurement technologies within this radar space, they both measure distance. Both a pulse and a frequency modulated continuous wave radar will measure distance. They measure distance between the antenna and the product surface, and it's a speed of light based measurement. So those fixed values I had shared with the dielectric constant, the permeability, the speed of light, we really take this for granted. Within the different radar technologies, though, there's a different critical variable that's being measured. So in the case of my pulse-based radars, my distance is a function of time. With a pulse-based radar, the one variable that we're measuring is time. My speed of light is assumed. My distance is measured directly based off the time. With a frequency modulated continuous wave radar, I'm not really measuring time anymore within the device. The way that these radars work is I'm constantly sending a frequency, and at the same time, I'm constantly receiving a frequency. So I'm just calculating distance based on the frequency difference. So this is technically a less direct or indirect method to measure level as compared to a pulse-based radar. At this point, I do like to tell people that from a commissioning standpoint, fortunately, all of the stuff on the right side here happens behind the scenes. All we really have to know from a basic setup standpoint, or what we would tell people during a technical training, a hands-on type training with the devices, is we really have to know critical values like the empty distance, the full distance, the levels calculated, at least from a software perspective, in a very similar manner for the user interface. So we hit a critical asymptote with pulse-based radar. I've got my pulse generator. I trigger an impulse. And what this impulse is it's very much, it physically looks like an electromechanical bullwhip. So I take this whip and I fire this whip and I shoot this signal into this antenna, down through the antenna, down into the tank, and I start a timer. I'm measuring the time that it takes to leave the antenna, reflect off the product surface, and then get captured again by that same antenna. This happens in an order of nanoseconds, typically, depending on the height of the tank, depending on the level in the tank. This is a nanosecond measurement. So I hit that critical asymptote here when it comes to generating a more nanosecond accurate clock. At a certain point, that clock and that accuracy in nanoseconds becomes, let's say, critically expensive or more difficult to manufacture in a repeatable manner. So this is a direct measurement. It also gets expensive as we try to get more and more refined when it comes to accuracy, fractional millimeter accuracy specifically. We compare this to a frequency modulated continuous wave radar. I'm constantly modulating this frequency. So it's no longer shooting a signal down and catching it in that electromechanical, that bullwhip fashion. I'm just sending a signal and I'm taking it from, say, 72 to 88 gigahertz and then throttling it back down, throttling it back up. It's a linear increase and decrease. I'm always sending a frequency and I'm always receiving a frequency. So instead of having to measure that fractional nanosecond time difference, I'm basically just using a frequency mixer. I can separate out that intermediate frequency and I end up with something that's mathematically a bit over my head. I did not do well with Fourier transforms in college. But once we have that formula is repeatable and it's very easy to make it quite accurate. Sorry if I'm being fairly self-deprecating, it's because the physics here fascinates me, but it was not my strong point academically. When we say what's new with new radars, they're very efficient. The measurement itself is we no longer need that pulse generator. So if you look at that kind of chip over there to the right, and then you look at the electronics specifically, we would traditionally need that, call it the transmitter electronics. That's where my signal impulse gets generated. That's typically connected via a high frequency cable into the back of the sensor electronics in the antenna. So we'd end up with kind of a 3-part measuring system. And those 3 parts are all very sensitive to anything that could change. Now, if I look at what the newer radars bring to the table, my sensor module is it's much smaller. So the measurement fundamentally takes place now on a chip, not a semiconductor chip, but a chip on the order of, a 1/2 inch by 1/2 inch. For those that are involved in functional safety, anytime we reduce electronic components, less possible things that can fail, in particular things that can fail in a dangerous or undetected way, our functional safety data gets much better the simpler the measurement gets. If we look at our frequency bands today, the companies that really focus, that specialize with radar, you'll typically see radars in the C band, K band, and W band. Now, I already kind of teased that there's only really one radar band left to conquer on the high end. So what is the driver as this barbell gets wider and as we push to the right? The single biggest thing, at least for showing people or explaining, why is higher frequency being so rapidly adopted and why is it being so rapidly developed, is that narrow beam angle concept. I can use a really big antenna with a low frequency radar. If you've worked with 4 or 6 gigahertz radars in the past, we're talking very large horns that are either large metal cones, or in some cases, large parabolic antennas that are really needed just to start directing more of that energy downward towards the product. So you'd see like a 6-inch antenna, you might have a beam angle of 23 degrees. Now, if we increase the frequency and we look at something in that 26 gigahertz range, now I don't need a 6-inch antenna, but if I have a 3-inch, my beam angle's down to 10 degrees now. So I don't need quite as large of an antenna to get that signal down into the tank. I'm able to get, frankly, quite a bit more focusing without having to stick what looks like a boat motor inside of the vessel. Now the real appeal with higher frequency is now with an 1.5-inch antenna, I'm talking about a 6-degree beam angle. So with a higher frequency, I can have a smaller beam angle, even with a smaller antenna, a smaller process connection, whether it be a vessel flange or even a threaded port on a vessel. It also makes things easier to specify. So I'm not as critical, I'm not as concerned with the tank wall effect. If I keep my signal tight, I don't have to worry about losing any of my usable gain in obstacles. But the other critical thing is if we've got things that are hazardous or toxic, or vessels that can't go out of service that are under pressure, we can install in tall nozzles or nozzles with, in some cases, one or multiple valves to be able to isolate from the tank. We also are able to capture longer measuring ranges and measure both liquids and solids with lower dielectric constants. From a technician standpoint, if you're worried about false echo suppression or not locking onto false signals in the tank, it can make commissioning quite a bit simpler too if you're seeing less noise or seeing less tank geometry and merely shooting off the product itself.
Question, Xander.
Yeah.
Based on this, do we see radar level technologies in LPG tanking? And I'm talking mostly shipping. Do we see that, or is it not useful in that application?
LPG, yes, but not quite LNG yet. And I'm not sure, but in terms of like petroleum distillates, LPG, yes.
Yeah, I'm thinking the maritime application where, off the coast of Louisiana, where we have terminals that are filling, LPG tankers for shipment to Europe, right? And wondering if they have these radar level sensors in the ships or on the ships.
I would probably have to look up specific examples. I know, for instance, it's a struggle because I focus on the Midwest.
Yeah, I appreciate that.
So when we do, for instance, liquefied natural gas, I know that we hit a critical distance because the dielectric's low.
Sure.
So for liquefied natural gas, for instance, I know that we can use these devices as like a high level alarm or high level interlock. but we wouldn't necessarily use them in a 120-foot tall LNG tank.
Gotcha.
But in terms of the maritime applications, I mean, I don't know. I don't have any specific experience offhand.
That's okay. Thanks. Appreciate the ability to ask the question.
Absolutely. That's the thing. I can, it's interesting being a Midwest resource because people all over the globe will ask me questions about soybean meal or other agriculture type products. And then somebody will mention something that's either offshore or, involved in major maritime shipping. And I just, I give an answer like the one I just gave you.
Xan, this is Patrick. The one LPG facility locally here we did work on, but it was long enough ago, as in 5 to 6 years ago, before more modern 80 gigahertz had come along. And the other major thing that had played a part there is that most of those applications carry a lot of NTEP or custody transfer certification requirements as you're filling and transferring and billing against those meters. And the certifications don't always follow as closely as the technology. So we ended up in plumb bob, servometric devices in those cases. But
Yeah,
that, hopefully that's some added context.
Thanks, Patrick. Yeah, and we have another question here.
What about, so we refer to the Midwest, obviously agriculture is a huge component. Are we doing anything around large scale, anhydrous storage or other farm-like substances, materials that, potentially have a hazard effect?
Yes, and you're also touching on something I'm going to get into here with anhydrous specifically. So there are some critical things here. As I talk about all that's good, I also want to touch on some of the exceptions.
Excellent.
And ammonia is one of our favorites for a couple reasons.
Thank you.
This is a nice segue too with the LPG question and the less reflective media. The higher frequency, we have a higher reflection coefficient, especially in medium, both solid and liquid with small dielectric constants. So we get a faster separation, we get a faster measurement when we go from, say, a tank bottom, an empty tank bottom, to a thin layer of these low dielectric products on top of it. We get quick level detection at minimum quantities. And this is really due to the fact that I'm getting much more reflection off the low dielectric and much less that gets permeated or transmitted through that low dielectric. So we're able to measure lower dielectric products quicker. Now, in order to give some concrete examples, some real world examples here, I have to talk about echo curves for anybody who's not familiar, or if you are familiar, it's been a while. What I'm going to share with all these examples is it's a snapshot of what the radar sees inside the tank at a certain time. This includes everything from nozzle effects, the tank wall, tank bottom obstructions, the product surface itself. It's going to give me information about the distance, how far away the reflections are, what the strength or the quality is, the amplitude of the reflection. It's also going to show me what the noise level is. So it's almost like a signal to noise plot over the full span the device is set for. This is kind of our leading indicator for quality and reliability of a measurement. And it's really invaluable for troubleshooting, being able to see exactly what the device is seeing. If you look back at some of the old training materials, we would show things like this, where we've got our radar, it's generating its pulse. My plot over on the right is going to be rotated 90 degrees to the left, but you can see the amplitudes on this particular kind of hypothetical example. I see some amplitude off the level switch, see some amplitude off the agitator. Down near the bottom, I can see some signal amplitude off my kind of heating coils. And all the way down at the bottom, I see another little hump where my level echo is. Also want to point out that time of flight radars, pulse-based radars, they physically look different from a frequency modulated continuous wave radar. When I talk about that electromechanical bullwhip or that impulse that generates that microwave signal that launches that pulse down into the tank, I can actually see that in that near field. That's the orange area on the plot. So on the left, you can actually see where that signal impulse gets generated. That's up in the head of the transmitter. So I can actually see how that looks over time. Now, if I get rid of that pulse, if I get rid of that launch, and I go to a continuously modulated frequency, now I have a flat launch. So that FMCW radar on the right, I no longer have that big impulse from that signal generating. A lot of cases, it just looks cleaner. In some cases, that cleaner look can really help us with regards to signal strength and reliability. These are some of my favorite examples. I just saw another one of these a couple weeks ago, but this tank is a lot like our example. It might even be a little bit worse. I've got a 2-stage agitator, some spray balls. I've got heating coils, concentric heating coils that are really a foot apart. So from the ID of the outer to the OD of the inner, I've got 1 foot of space to be able to get a microwave signal through. In this case, we happen to have a flange that's installed directly in the middle of those two. And this was an application that frankly probably wouldn't have been possible installed from above without this high frequency radar. So even with all that internal geometry, I have a relatively flat baseline with 1 strong peak. That strong peak coincides with our level. When you're looking at installation specifications for things like the nozzle height, you'll notice that with a narrow beam angle radar, the allowable height of your nozzle increases dramatically. So instead of having to think of the rule of thumb that I always think of, the nozzle can only be twice as tall as it is wide. So instead of going in and thinking, if I have a 3-inch diameter nozzle, I have to be 6 inches tall or less, we start seeing these frankly comedic numbers when it comes to installation requirements. The examples here, I've got about, I believe it's a 42-inch nozzle, 2-inch in diameter on the right. And then on the left, we've got a nozzle that changes diameter a couple times, and there's a ball valve in there for being able to isolate. In this case, with a 4-inch diameter nozzle, again, hypothetically, we say if your nozzle is going to be 4 inches in diameter, it can be up to 88 inches tall. Because there's no signal launch, these devices work particularly well in small vessels. So I don't have to deal with a big cascading signal launch anymore and trying to measure that fractional nanosecond to be able to reflect off a surface in the near field and then catch it at the transmitter. When I take this FMCW concept and I put it in a small tank, I get a much cleaner definition and a much more accurate reading, even with low dielectrics, small vessels. speaking to the universality, we're onto something here. We think we've got a device. This could be universal because we can take that same exact device and now we can put it in a 234-foot stormwater runoff pit, which you may have water on top, you may have plastic bottles, clothing, cardboard, you name it. And now I've got the same device that can work in a 20-inch tall vessel or a 234-foot pit. I promise I'm getting to the exceptions here. Because before I do want to highlight, why we're spending so much time and why these are so readily adopted. There's one more physical symptom when we increase our frequency. We shorten our wavelength. This doesn't really matter for a liquid, but where it really benefits us is with solid. The non-contact measurements in solids have always been a challenge. With lower frequency radars, you had a wider wavelength, and you ended up not getting a lot of signal back to the transmitter. With something like a laser, you might be able to measure the solid level when you can physically see the level, but certain measurements really struggle with dust, like laser and ultrasonic, where the dust can attenuate that signal. What we notice right out of the gate with 80 gigahertz in solids is that we get more signal back to the transmitter. The best analogy that I've heard is it's like taking a flight of stairs, and if you've got a golf ball or even a tennis ball and you throw it at your stairs, there's a high probability that it's going to bounce back to you. But if you take a basketball or a beach ball, there's a pretty good chance that if you throw it down, that ball's not going to come back. It has a high probability of going laterally. I tell people today there's almost no reason anymore to use a guided wave radar with solids with the signal improvements and the reliability with non-contact. And we see that when we look at sales numbers as a company, not just as our company, but the market as a whole. I look at Level Technologies here. That green band, that is just non-contact radar. So it's strong and it's over proportional. Whereas for technologies like ultrasonic, it's flat, in some cases even decreasing. So radar's truly becoming a dominant technology in this space. And what even better, it's really simple now. Maybe simple with a few asterisks. What we end up with is we really have these primary ranges where we're looking at where radar measurements take place. So on the far left, we have guided wave radar, radar that follows a physical probe. These devices are still exhibiting plenty of use cases in industry. So interfaces, liquid-liquid interfaces specifically. Also applications where the dielectric constant of the vapor space can change. So if I'm measuring high pressure steam or high pressure ammonia, once I get above 300 PSI, it actually starts to increase the dielectric constant of the vapor space. There's ways that we can use guided wave radar that correct for that and can compensate for the polarization or the increasing dielectric constant of the vapor space. At the same time, we know the left side of the barbell still has use cases. We still use guided wave radars. What we notice as we generate new frequencies is that we maintain a barbell effect, but the barbell gets wider. So all the examples I've showed, based on our experience, all these new options, narrow beam angles, better reflection off solids, we'd say 90% of applications, level applications, we could do with 80 gigahertz. But the devil kind of lives in the details here. You'll notice I've put bold around that advantages for 26 gigahertz. It's the best choice for certain solvents. Well, what does that mean? In order to revisit that permeability, that mu value, I want to bring up the one historical example that we've known for the last 20 years. If you look at any major manufacturer of radar and you look at their radar in this frequency, they will say, do not use this in ammonia service. That includes both anhydrous, but also aqueous. So there's a coincidental bond within the ammonia molecule itself that will actually absorb a 24 to 26 gigahertz radar signal. When I was putting this together for the first time a year and a half ago, I thought, you know, there's got to be some good scholarly articles or ways to look up, you know, where is my permeability? Where is my mu value? Where is it less than 1? You know, I can look up a dielectric constant of any fluid you could give me. I could find the dielectric constant within 5 minutes. And I thought, I want to try to do the same thing with this mu value. Kind of teased this earlier. I am not a good student of physics. I would end up finding articles like this. I kept getting back to things that I couldn't wrap my head around and that frankly aren't necessarily valuable to an instrument engineer or a technician who's trying to look this data up. I could find some things for ammonia, but I would find articles like this, more like space studies, things around academia and the study of our cosmos. But there's got to be somewhere that you can find these mu values for different frequencies to figure out, you know, how do you avoid this exact phenomenon? And I said, not a good physics student. I was looking at this going, channel maps, intensity maps, ammonia emission. This is what this type of data looks like. My 24 gigahertz continuum emission is shown as dashed contours, except the bold dashed contours, which highlight regions of ammonia absorption. I knew that this was going to be hard to come up with specific examples or to research anything in advance, just because it's not intuitive. No one's done this research yet. But I kept finding my way back to NASA. So the allowance of radiation, non-ionizing radiation in our case, to pass through a gas, that permeability constant, it varies with the wavelength and the type of radiation, but it also varies based on the gas itself, what's in the vapor space. We tend to know the areas of the electromagnetic spectrum that are absorbed by atmospheric gases because of issues with early aircraft instrumentation. So we know now if you're using instruments in an aircraft or in spacecraft, you have to be tuned to specific frequencies to avoid absorption. But a lot of this stuff happens as the result of plane crashes. So how can we be proactive here when we're trying to figure out, you know, radars and which frequencies to avoid and which particular applications? Well, we did the first thing that any inquisitive mind would do when we came up with a radar frequency above 26 gigahertz. The first thing we did was put it in ammonia service, and we said, "Oh, great! It works. We get a signal, so we're in the clear." But that's just with one particular coincidence. I was sitting with a bunch of my colleagues, some in R&D, some in sales, but sitting with a bunch of colleagues, I think it was 2017 already. And I'm listening to my colleague from Charlotte, and he's talking about man, it's like this radar was totally blind. And I thought it was a bad radar. We swapped it out. And then the second one was blind. What's even worse, it's acetone. It's polar, it's reflective, it's got a dielectric constant like water. We should be getting a huge signal off this. And we end up, our signal to noise ratio, our echo curve is just a flat line. What in the world? So we find out in real time that this 80 gigahertz frequency has a coincidental vibrational bond with acetone in the vapor space. So acetone, if any of you have bought any type of paint remover or a goof off, if you spill acetone, it's very volatile. It enters the vapor space. That's what I'm looking for. It has a low boiling point, so it's very volatile. So with something like acetone, we know we can use a guided wave radar. We know we can use a 6 gigahertz, a 26 gigahertz. It's just this weird coincidence that takes place with this 80 gigahertz frequency. To make things even more challenging, if I take acetone and I mix it with something else, so it kind of decreases the volatility or decreases the presence of acetone in the vapor space. In this case, I take acetone and mix it with isopropanol. We're back to being in a decent place. I'll show you one of mine. This was at a chemical customer on top of a tank. If you're familiar with ACN, it's not particularly friendly stuff. But I had my, oh boy, what am I looking at here? We actually had a valve on this tank to be able to replace the unit without a high level of exposure. So we swapped out the device, and the device that we pulled worked perfectly on the benchtop. And we find out only at elevated temperatures for this one, only when the temperature gets above about 140 to 150 degrees do we start to have this absorption take place. So a few days in the summer, we get some higher temperatures, maybe a pump runs on recirc with low level in the tank, we end up with this scenario. But it's like the device goes blind and it stays blind. So as we're out in the field and we're learning this stuff, vendors don't reflexively go into customer sites and talk about all the different places you can't use, especially new technology that we like. So different manufacturers they'll kind of cover their bases in different ways. Some manufacturers will actually build it into their configuration tools. So if you're configuring a radar on their website, you might have to actually say early in the process, if you're handling something that has acetone or something that has ammonia. In some cases, they'll be in product data sheets, maybe a list of non-compatible media with a given radar frequency. But this isn't necessarily something that you'll see on page 1 or on the front page of the website. What's been such a challenge is that even with known molecules that can cause issues, it's difficult to predict. This is heavily dependent on the temperature and the pressure. The absorption of this microwave signal, it's not a vibrational bond. The vibrational bonds of these molecules is orders of magnitude higher. So this is a rotational bond that occurs at these frequencies. So what we've observed is these potentially absorbing substances, especially with the highest frequencies, they tend to have polar bonding regions and they tend to have low boiling points. So we tend to have a saturation of that vapor pressure with the molecule that causes this issue. To this point, we've observed it primarily with ketones, but also some epoxides, some halogens, and at high temperatures, some benzene and benzene derivatives. What's so tricky is it's not a catch-all. So I was kind of confiding to another colleague about, man, I wish I could use this in toluene. We have a lot of atmospheric toluene tanks at our chemical customers. A lot of times they have maybe an 1.5 inch threaded connection on top that I'd love to be able to put an 80 gigahertz radar in. And then I hear one of my other colleagues goes, oh, I can send you examples. We got hundreds of these in toluene service. Sends me this snapshot there below. And I'm grappling that, toluene is on the list of media where we've identified problems, but yet our installed base is quite large and we don't seem to have a lot of problems. It's a function of the boiling point. So oftentimes, if we're working with a pharmaceutical company or if we're working with a chemical company and we're dealing with atmospheric storage or processes that don't get particularly hot, we might educate them about, hey, if you end up heating this toluene, if you end up approaching the boiling point, we could have signal attenuation. It truly becomes this ultra consultative approach where you want to be able to use the best possible instrument that gives the best performance, the simplest setup over the life. But you have to be able to share these details around things like the operating temperature of the process, the potential future solvents that could be used in a given tank. We can't always guarantee that a storage tank is going to have the same solvents year after year. So it ends up maybe resulting in a few additional questions, but also making sure that we're doing our due diligence in vetting these installations. But what can we do to keep up with our findings from the field? You can see in this case, we update our product data sheets pretty regularly. We're on revision. I haven't been keeping up with this, but revision 7 after a few years to be able to capture these examples. I think this is more apt. Can feel a little bit like a crash test dummy at times. So there's a few things that can help us. And I do want to talk a little bit about, the ways to verify that the instrument may not be the issue, but it could be an absorbing gas or even an unknown absorbing gas, something that's affecting that permeability of that vapor space with that radar frequency. Along with the simplification of the electronics, there's a very high drive to have a much higher diagnostic coverage of those critical components. So we want to take this measurement and we don't just want to check the output of the device. We want to make sure that every single piece of that hardware is operating exactly as it left the factory. So this starts with everything from the loop itself, things like the terminal voltage, the current, any type of loop diagnostics, but also the signal quality, the analog path, the intermediate frequency signal, everything that really goes into the heart and soul of that measurement. We want to be able to trace that over time. So inside of that transmitter, how do we take something that ultimately leaves the manufacturer's hands and ends up at a different manufacturer at a customer site? And how can we do things like detect random failures or detect things like drift caused by aging, or even detect things like systematic faults? That could be we put the radar on the acetone tank and right out of the box, we're getting no signal back. how can we find not just random hardware failures with a high degree of certainty, which are particularly dangerous, but also find things like process-related systematic faults. That could be anything from buildup on the face. It could be, I installed this in a tank that had some alcohol-based solvent for 8 years. And after 8 years, we decided we're going to put acetone in that tank instead. So these are both faults that occur inside the device, but also outside of the device. And then how do we make it traceable? How do we take something where it's one thing to leave the factory and say, okay, now remember everything inside of you and how it was set up. But how do we verify or trace something back to the calibration cert that it left the factory with and show definitively that it is or is not a hardware versus a systemic or process related fault? The cool thing with these smaller electronics and making things more energy efficient is we can do stuff like this, where we can put a redundant set of that high frequency circuitry inside of a device. So I've got a high frequency oscillator, and then I have a sampling oscillator. I compare these two measurements, and even though they're not time-based, I can think of this like if I had two watches. I think Patrick has a story. I guess we're a half Swiss company, but I guess somebody really likes watches, so he wears two at the same time. The idea is if I've got two different high frequency systems, one's performing the measurement, one's purely a control. If I notice any one of those start to drift at all, I can trigger an advance warning that my level or my measured distance is going to quickly go out of tolerance. Even though there's only a 50% chance that it's the watch that we really care about, or the high frequency circuitry we really care about, this allows us to have some type of traceability inside of a device that frankly is challenging, if not impossible, to actually calibrate. So I take two high frequency generating chips, slap them in a single device, got some type of factory standard that's traceable to my international standard. This is really what goes on to the calibration certificate of the device itself. We've got our externally traceable reference for these frequencies and for the measured distance when we do a factory calibration. And those two frequencies are really validated or traceable to the original device calibration. So when it comes to the safety instrumented system lifecycle, the calibration certificate, and in some cases, even the verification report meet the requirements for lifecycle documentation. So being able to do a proof test or inspection, this admittedly would be a partial proof test, but the high diagnostic coverage and the redundant circuitry within a given device can often be used to extend a proof test interval, at least on the instrument itself, speaking independently of the system. So that's great. What next? What next? When I originally came up with this presentation topic for ISA Will Do Page in Chicagoland, I knew that there were higher frequency radars being developed, but I didn't realize how soon. So we're already developing, I'm sure many companies are developing even higher frequency radars to capture even lower dielectric constants with sharper peaks, better signal to noise ratios. But where does this beam angle tank connection race, where do we end up here? we're running out of different radar frequencies. Do we go to an even higher frequency measurement than radar? And most importantly, the crash test dummy example, who's doing the research? Who knows where these devices will and won't work? At this point, it's really tribal knowledge and knowing where you've been bit in the past, at least as from the instrument manufacturer's perspective, that's how it feels. And geez, do we need to continue to be crash test dummies? What can we do to avoid flying through the proverbial windshield on a radar application, scratching our heads on top of a tank with potentially toxic or hazardous materials in it? But I will admit, having a threaded device with a 1/2 inch thread, a tiny thread, 180 gigahertz, a 6-degree beam angle. Wow. It's easy to see the appeal. But, my first question is, where is it not going to work? And I have a feeling that we're going to find out. That was what I had planned. I know I got a meeting invite for an hour and a half. I tried to keep it to an hour.
Splendid, Xan, thank you. That was splendid.
Well done. So I have a question. What, if any, in the certification process, steps are being taken to test for adversarial conduct? A lot of these devices are counted on to maintain safety, stability. The loss of some of these operations could have a cascading effect to the economy, national security. My question is, what, if anything, are the manufacturers doing to, as part of the safety testing, include a potential use case and adversarial use case?
I lost a couple critical words there. I think I got the gist of it, though.
Too long didn't read. What are you doing to keep the bad guys from blowing stuff up?
Gotcha. Okay. I thought it was going to be a slightly more nuanced. I do have a slightly more nuanced answer to that when it comes to like, are you talking cybersecurity in particular, or more on the functional safety side?
Both.
It's both.
Both digital adversarial action as well as physical. For example, if someone was an inside bad actor at a facility, they had the ability to manipulate. Are there detection mechanisms? And obviously, I don't want you to disclose any of that. But I
Gotcha.
like a general question: is that an area of concern, and is it getting attention and focus?
Absolutely. I am not as familiar with the IEC standard around cybersecurity. I want to say it's like 62443.
Yes. Well done.
Well, that's an exercise in memorization, not an exercise in familiarity. I am aware of the cybersecurity standards around the instrument that we conform to. I am far more familiar with the functional safety standards. I know, like, especially when our devices have Bluetooth, which Bluetooth is something, it's another trend. I didn't talk about it one iota today, but the question commonly comes up with Bluetooth and cybersecurity, and how do I prevent somebody from being able to configure an instrument from within, 30 to 50 feet.
Right.
So when we talk specifically about Bluetooth and the IEC standards around cybersecurity, what we'll often talk about is the initial encryption. So how do I gain access to the device for the first time? That's not even a change parameters question, but how do I gain access to that device? What we've done is we've copied the mobile passport security. So we stole something from the Fraunhofer Institute.
Mm-hmm.
So it's got to be within an app and with that specific device password. But there's intrinsic problems with that too, especially when we need to really lock instruments down. Thinking specifically about those safety loops where we don't want somebody going in and tweaking damping values because a signal's a little noisy. So even beyond that initial login, the ability to set software locks, secondary levels of password and lockout behind that has been critical to the acceptance or the adoption of some of these other methodologies like Bluetooth, for instance. The other point, I struggle a little bit with the functional safety thing, especially now that I work for an instrument manufacturer and not an end user. Because when I was doing projects with Xan, it was highly ill-advised to do a partial proof test. You can walk up, you can pull an instrument, you can throw an instrument loop, you can even bypass the instrument and make sure that it works under test. But what about the critical control element that's going to shut down the process? So I'm just talking, again, theoretically, but from that instrument's calibration perspective, that's all I can attest to from regards to functional safety, because I'm still a huge advocate for doing full proof tests and engineering bypasses to functionally test those systems as often as logically possible.
One follow-on to that, signal interference. So, bad guys in the parking lot, it's got a sig generator, is introducing all sorts of chaos to the spec. Is that something that has been considered? Again, don't disclose any specifics, but is that something that's been considered and folks thinking about those avenues, given the time?
What I think of right away, I don't even think we were the first ones to do this. I think Rosemont has something similar. But I've noticed when I do odd things to the loop, if I've got an instrument, and I noticed this when I was messing around with, I bought some cheap 24-volt power supplies off of Amazon, and the instruments didn't like them too much. It wasn't anything like the amount of amps or necessarily the amount of milliamps, but the instruments themselves, some of those internal variables, like those loop diagnostics, if you're starting to notice the addition or the subtraction of not just voltage, but the milliamp itself, the resistance in the loop, I would think without going into, well, it potentially could go into a fault, but the instruments will usually give you some type of maintenance required or out of spec type of message. So the hope would be, if it's a critical safety system or critical safety interlock, and you've got a device that's saying or outputting some type of diagnostic message like, hey, come look at me, or maintenance required, the device may be able to catch that within the loop itself.
Thank you. Very well articulated answers.
I appreciate the questions and the feedback too. This is stuff that I think about all the time, not just in the context of radar, but safety instrumented systems. It's just been a long time passion.
Well, if you ever want to nerd out, I'm sure we can figure out how to swap contact details. It's passionate as well. I'm the guy that breaks stuff.
Nice.
And so we've been passing some notes back and forth back here about how could this radar instrument be affected to cause something catastrophic? Could the radar band be increased, or are the devices set for 26 gigahertz, 80 gigahertz? Or do you have circuitry that keeps it at those frequencies within a guard band of the center frequency? Or can you manipulate the frequency to do other things? Maybe gel some material, make some material that you're trying to measure, and all of a sudden you change the frequency, it changes the absorption characteristics, and all of a sudden you're heating the material.
The reason why that doesn't happen is just because the available power
That's what I thought.
available power for the measurement, we're only giving you like 14 milliwatts.
Yeah,
So it's just not enough to physically change. I'm sure we could find some examples somewhere where you could actually cause a physical change in a material with 14 milliwatts, but it's just so little energy functionally that it's not something where I've got this aha or this example I can even pull from.
yeah, so there's some inherent safety built in due to a limitation of radiated power.
Right.
That's.
That's gonna make me so.
We do guardrail the measurements quite a bit. So every manufacturer is going to have some version of this. The time of flight radars, so the radars where I'm generating that impulse and shooting it into the tank, you have to use some type of static coding on those because you're shooting so many so rapidly that you have to be able to statically code each signal. So if you're getting them back 10 a second, you're able to delineate or separate the useful signal from the signal that came right after it. And also avoid crosstalk with other devices on the same tank, but also avoid any other devices that operate in that band. With the frequency modulated wave radars, in a lot of cases, that actual modulation, so the band that it's going back and forth, will be dictated by the distance. So the larger the distance, the less you modulate the frequency. So if I'm in a tank that's 12 inches tall, I might be going back and forth from 72 to 88 gigahertz very rapidly. But if I'm on a 400-foot silo, I'm only going to go back and forth about 2 gigahertz in either direction. I thought about this, and I get in so much trouble because I'll pull something up from R&D, something that we'll have in 2 years, and I really want to share some of the stuff that's maybe a little bit further down the road, but I just can't yet.
Thank you. Again, well articulated answers and very informative.
Thank you for the feedback. Especially with a group of people, I don't necessarily have the same level of rapport, or I haven't known this group like I've known the ISA will do page section for so long.
We're geekier.
I appreciate that.
Quick couple of questions. In short, what allowed things to go from, just a handful of gigahertz to now 8 gigahertz? Like what technological change made it possible? And what kind of computational modeling do you do to try to look to avoid crashes? Like simulation of different materials, or?
I believe most companies who play in this space would freely admit that the technology is stolen from LiDAR. This was a adaptation of the technology for autonomous driving that got applied to an industrial measurement. And there were even some companies that decided not to invest in the technology, and their whole point was, well, this isn't a valid industrial measurement technology. This is tech that's stolen from the automotive space. Those same companies that said that a decade ago are now investing in this technology. So it started off in that space, and frankly was not stolen, but co-opted into this space. In terms of the computational modeling, we do not do it. I don't know if anybody does. All of these exceptions and all of these examples are derived from the user experience, at least to this point. So the field trial stage before something goes to market will normally do between 18 to 24 months of evaluations in different countries. And whoever chimed up earlier and said, if you ever want to break something, that's really our, hey, let's break this window. Let's take this device, let's figure out where it doesn't work, figure out if there's any software bugs. If we don't put something in something that will interfere or break the measurement in that trial period, kind of opened the presentation, this is an arms race. As the manufacturer, we're trying to get this, if there's a valid use case, we're trying to get this stuff to market. So it's kind of a double-edged sword.
Okay. The reason I asked that last one is, in college, I tried working with a Fortran simulation of electrons, passing through different materials to measure, best case for sensor efficiency. You just put in files of different materials and figure weaknesses and stuff like that. And I know this is very different, but I was just curious if there was anything that's used these days to try to simulate what effects you might get from using the radar and different.
Gotcha. Now we have some plates that we use, but the plates are of I'm not sure what the material is. The plates have a permeability less than 1. So we have plates where we can put them in front of the radar to attenuate the signal, but we don't necessarily know all the
It
different
looks like we
potential
just lost the main
materials.
presentation.
Still hear me?
Yep, I can see the presentation as well, at least on my end.
I noticed I can't see on camera anymore.
And you have a charger that doesn't have a LED on it, huh?
Yeah,
Yeah.
isn't that lovely?
Yeah.
I work at that.
Oh, that would do that.
Or the little cord, the plug that goes into the laptop sometimes will light up, and
Yeah.
that's what mine does.
Like,
Scale.
no.
All you can do is look at your little battery symbol and see if it's charging.
What is all this project, by the way? Jonathan. So that's super cool. Using Fortran to do that, that's freaking awesome.
Well, it's something someone else had, they developed it in Japan, some university there, and they were sharing freely. In fact, it would give you like a whole manual and all that if you just said you wanted to do research.
Really?
Yeah, it's called electron gamma shower.
Okay.
Okay.
Died on us.
So that's me. Hang on.
I have a camera feedback, at least on my end.
All right, I think we're back up and running. Sorry about that, folks. Thank you so much.
Yep, I see that your camera just came back on, so all good.
Our grid failed.
Yeah.
Any other questions or are we wrapped?
I think we're wrapped here.
Well, I actually, if you had to answer my question in relation to like, even if your company isn't doing it, do you know of different things in the field? Modeling to know what you can expect to get for different gases. To this speed.
In terms of permeability or transmissivity?
Yeah.
I guess
All
my
You mentioned different things like the rotation of molecules. There are many different effects that need to be accounted for.
I guess my answer or my fairly blunt no is just based on, in some cases, we know that these physical effects exist without having to do any modeling. And yet I was observing the other week that there's a company that recently makes an 80 gigahertz radar, and they have no mention of acetone anywhere on the product page, product data sheet, website, etc. So not only are companies not doing high-end modeling, in some cases, they're not even researching other companies that make these measurements and what they say to avoid. That's the scary part of this whole equation. Now that might change, but it's not something I'm privy to anybody doing.
Well, that's something interesting, and that are you,
Am I? Yeah.
Are you?
Yes.
Excellent. Then that's something you could submit as a suggestion to the Technology Evaluation Committee as a potential standard or exception. If you haven't already made that suggestion.
I've toyed with the idea of like having some type of sanity check, like maybe below on a standard ISA data sheet for a radar based transmitter. Could you have something where there's a mu value and like it would just be it'd be hard to look up. So I've kind of toyed around with this idea, how do you take a suggestion or a concept like this and make it so that industry as a whole can improve? It's a good idea. I should put something together and try to start a broader conversation as opposed to just communicating with our clientele and other nonprofit organizations like ISA. I should work with ISA closer on this, admittedly.
Be great. Yeah. The Technology Evaluation Committee has a variety of things on our plate. In fact, I put some things in several years ago, like one word suggestions that I have to kind of vet out. I have to change it, modify it, update it, and make it relevant or recommend that it be eliminated. But what you just described as a method for, gaining some, standards across radar. That would be great.
Yeah.
All right, any other comments?
I think we're good.
Okay, thank you. Yeah, thanks a lot. Have a good night.
Thank you, everyone.
Thank you all. Great questions. I
Thank you.
appreciate the discourse. See you guys.
See ya.
Thanks, guys.
That's giving us a little bit of reaction. Pete Static, I was gonna suggest, Katie, that you mute Pete.
Yeah, I was trying to towards the end there.
Yeah,
Because you know Pete or?
yeah, somewhat.
As a radar man of old, what do you think? Not that you're old, but you did.
What I'm wondering is, how would you